Hello, everyone. With your board exams just around the corner, I know things can feel a little intense. So let's just take a moment, relax, and do a quick and powerful revision of a chapter that is so important, carbon and its compounds. We're going to make it really simple. Okay, let's start with a simple question. Just think for a second. What does the food you eat, the books you read, and even you yourself, what do all these things have in common? You guessed it. The answer is carbon. It's the one element that connects everything. It's the basic building block for all life, from the smallest plant to you and me. It's just everywhere. So that brings up a really important question. What exactly makes carbon so special? Why do we call it the element of life? Let's find out. Now, here's a fact that might actually surprise you. For an element that's so incredibly important, there's not that much of it around. In the Earth's crust, in the form of minerals, carbon makes up just a tiny 0.02%. And if you look at the atmosphere as carbon dioxide, it's only about 0.03%. So this is the main point to remember. Carbon's importance doesn't come from how much of it there is, it comes from its amazing properties. And that leads us to the real secret behind carbon's power. The heart of it all lies in one simple idea, the covalent bond. This is how carbon connects with other atoms. You see, carbon has 4 electrons in its outermost shell. To be stable, it needs 8. Now, it's very tough for it to gain 4 more electrons, and it would take a huge amount of energy to lose all 4. So carbon does something brilliant. It doesn't gain or lose electrons. It shares them. And this sharing of electrons is what we call a covalent bond. You can think of it like a strong partnership, a chemical handshake, where atoms share their electrons so that everyone feels stable and complete. And remember, these bonds are very strong. Just take a look at this diagram of methane, CH4. See the carbon atom right in the center? It's sharing one of its electrons with each of the 4 hydrogen atoms. In return, each hydrogen shares its 1 electron with carbon. So now, carbon has a full shell of 8, and each hydrogen has 2. Everyone is stable. It's a perfect example. This amazing ability to form 4 strong covalent bonds gives carbon 2 unique properties. And to make them easy to remember for your exams, let's just call them carbon's 2 superpowers. Superpower number 1 is catenation. It's a big word, but it just means self-linking. Carbon atoms can form really strong bonds with other carbon atoms over and over again. This allows them to form long chains, branched chains, and even rings. No other element can do this so well. And superpower number 2 is tetravalency. Tetra means 4, so because carbon has a valency of 4, it can form strong bonds with 4 other atoms at the same time. This opens up a whole universe of possibilities for building complex, 3-dimensional molecules. Because of these superpowers, even pure carbon can exist in different physical forms. We call these allotropes. For example, in a diamond, every carbon atom is bonded tightly to 4 others, creating a rigid 3D structure that makes it the hardest substance we know. But in graphite, the carbon atoms are arranged in flat layers that can slide past each other. This makes graphite soft, slippery, and a good conductor of electricity. Same element, just a different arrangement, and completely different properties. Okay, so we've seen how carbon atoms bond with each other. Now let's look at the kinds of compounds and structures they can build. First up, we have hydrocarbons, compounds made of only hydrogen and carbon. They fall into 2 main families. Saturated hydrocarbons have only single bonds between their carbon atoms. You can think of them as being saturated or full of hydrogen atoms. This makes them quite stable and less reactive. On the other hand, unsaturated hydrocarbons have at least 1 double or triple bond between carbon atoms, which makes them much more reactive. And here's a perfect picture of that. This is ethene. You can clearly see the double bond between the 2 carbon atoms. That double bond is the key. It's what makes ethene an unsaturated hydrocarbon. Now, this is where it gets even more interesting. We can attach other atoms or groups of atoms to these carbon chains. We call these functional groups. A functional group, like OH, is what gives a compound its unique identity. For example, if you attach an OH group, the compound becomes an alcohol. If you attach a COOH group, it becomes a carboxylic acid. The functional group decides everything. All right, enough theory. Let's see how all this works in the real world with something we use every single day. Soap. The magic of soap is all in its molecular structure. A soap molecule has two different ends. One end is the ionic head, which is hydrophilic. Hydrophilic means it loves water. The other end is a long hydrocarbon tail, which is hydrophobic. Hydrophobic means it hates water, but it loves oil and grease. So, when you mix soap in water, something fascinating happens. The molecules arrange themselves into these beautiful spherical clusters called micelles. You can see one right here. All the water-hating tails point inwards to hide from the water, while all the water-loving heads face outwards. So here's how it all comes together to clean your clothes. First, the oily dirt on your clothes attracts the water-hating, oil-loving tails of the soap molecules. The tails dig into the dirt particle. Then, they form a micelle all around the dirt, trapping it inside. And finally, because the outside of the micelle is water-loving, the whole cluster, with the dirt safely trapped in the middle, gets washed away with the water. And just like that, the oily dirt is gone. It's a simple but brilliant real-world example of carbon chemistry in action. So, we've seen how carbon's unique properties are just perfect for creating the complex molecules needed for life. But it leaves us with a fascinating question to think about. Silicon is right below carbon on the periodic table, and it also has a valency of 4. So what do you think a world based on silicon instead of carbon might look like? Just something to ponder. All the very best for your exam.